Okay, now we're going to look at the second type of isomerism, which we are actually calling stereo isomerism. We are saying this is a type of isomerism where the compounds have the same molecular formula and they also have the same structural formula. But the difference in this case is in the spatial arrangement of the bonds. So stereoisomerism is not related to the links and the bonds, but the spatial arrangement is more of interested in how the atoms are arranged in space, how they are arranged in space. And we are saying we have two types. The first one we're talking about is the cis-trans isomerism, which some people call the geometric isomerism. I was saying this occurs in compounds in which free rotation is prevented by either a double bond or a ring, whereby they are rigid, they cannot change, and therefore the compounds become different because of the rigidity of the bonds. Rigidity of the bonds. Okay. For example, when we look at this compound and this, because of the presence of a double bond here, therefore there is no kind of rotation. And because there is no kind of rotation, this compound is totally different from this one. For example, when you look at the fact that the carboxylic. So, like I was saying, we are looking at this example here. We are saying that when you look at it, you see there is a double bond for both. But this double bond prevents rotation. It prevents rotation, and therefore this compound cannot be like this. Because in actual sense, if this bond was to rotate, it means this carboxylic group would come here, the other would come here, and it would be like this exactly. But because the bonds cannot rotate, then we're going to find that this compound is rigid and is different from this. Of course, the difference is the fact that when you look at this, the carboxylic groups are on the same side, the hydrogen is also on the same side. That's why we call it cis. But in this case, in trans isomers, the identical groups are opposite or diagonal to each other. You look at the carboxylic group here is different from the carboxylic, is on this side, and the carboxylic group here is on this side. Another example would be when you look at carbon, double bond carbon. Of course, I can put here hydrogen, I put here CH3, I put here hydrogen, I put here CH3, and then I relate this one with carbon, double bond carbon, double bond carbon. I put here hydrogen, I put here CH3, I put here hydrogen, and I put here also CH3. Of course, when you look at both compounds, they are but2e. This is but2e. This is also but2e. But this one becomes cis-but2e. Why? Because the methyl groups are on the same side. Whereas this becomes trans-but2e because the methyl groups are opposite or are cross-sectional to each other. So the fact that this bond cannot change or cannot be rotated because of its rigidity causes this compound to be different from this one. But when you look at the structural formula, it looks the same. The molecular formula is the same, but they are isomers. Okay, now the last part of isomerism, we are calling it optical isomerism, in which case it occurs in compounds with 4 atoms or group of atoms attached to the same carbon atom, such that the isomers obtained do not superimpose or are not superimposable on their mirror images. And we are saying these kinds of isomers are called enantiomers. And I've given you a clear example there. When you look at this, of course, both of them, when you look at them, when you look at this 1, 2, 3, 4, they are butanol. All of them are butanol, but the OH is on carbon number 2 for both. Carbon number 2 for both. If you start counting from the CH3, the OH is on carbon number 2. So both of them are butanol, but when you look at the way they are arranged, in this case, there's one thing you're going to realize, that this one is a mirror image of this one. When you look at their arrangement, of course, if you remember a small physics of yours, for mirrors, you know, the image distance is equal to the object distance. And because of that, you're going to find that this methyl group that is attached to the farthest end of the mirror will also be on the farthest end. And this OH, so we are saying it is more like a retro inversion. You look at the image, the object that is nearest to the mirror, still in the image, it will also be the what? The nearest. So when you look at the compound, you look and you realize that this is an image of this. They are not superimposable, and because of that, they also become isomers. That is optical isomerism. So what you realize about stereoisomers is that their molecular formula and their structural formula, they look the same. But when you look at them in terms of their spatial arrangement, you realize that they are what? They are different. We have said for geometric isomerism, the spatial arrangement is coming because of the rigidity of the multiple bonds or rings in the compounds. But we are saying for optical isomerism, we are saying the reason for the isomers to become different is because one cannot be superimposed to the other when you consider them as mirror images of each other. So basically, that is isomerism. That's isomerism.